talk about regression. Going all the way back to undergraduate start, line of best fit, do we all know what that is? I've got a bunch of points. Something like that. Is that linear? Kind of linear.
And sort of.
Well, how much I can't do that point.
Yeah,
That's all right. I see why. So I've got this sample with 7 observations. I'm going to put the x-axis as time for a reason. Time series. What should normally be? Something that varies with time. Can you think of something? I have an example, but I'm going to use it for series.
Sales.
Sales. I guess I'll use the same over here. Line of best fit. So the y-axis, the dependent variable, varies with time. Y-axis. Call it the number of babies born in the US. We just need some time here, so let's start at 2000, 2005, 2010, 2010. And you might think that, well, why do I have here points that are close to each other? Perhaps I put 2006 in that 2005 range, even though it's wrong. For the sake of the example, let's just work with this. So what can we say about the number of babies born in the United States over time? It's been going up. Population has, risen and constantly rises. So it is increasing. And in terms of linear regression, we have a theoretical model, which we went over in applied stats. So do we remember what that model is? Y equals something plus something else.
It's y is equal to beta times by x plus epsilon. Or is that the real one?
Okay, got it. So what I'm going to do is write it as y of t. And I'm focusing on t because I'm going to make an association between this and what we're about to do. So y of t equal to beta. That would be all the regression coefficients. The independent variable is t plus epsilon t. That is the underlying model that we are focused on. So theoretical model, branching model, what say you? Well, that is the model. Let's put a parentheses here so that we know what is what. So y of t would be the dependent variable, obviously. The number of babies would depend on time. And time t is the independent variable. let's see if you paid attention in applied science. What is epsilon t? Epsilon.
The residual.
Very good. Residual. The part or the step when we call it residuals, when we call them residuals, occurs after fitting the model using the data. Correct? Before we fit the model and look at this theoretical part, it has a different name. Error. It is error. In other words, starts with the letter N, ends with E's, got half letter. Noise. And noise is what that makes this system not deterministic. In the sense fancy word stochastic, because time series are stochastic processes. But in simpler terms, what do I mean by stochastic? It is probabilistic. It is noise. That is responsible for introducing variation in Y of Z. We will talk about that in a second. Deterministic. If something is deterministic, we are saying that that particular process is fully determined. For example, if I didn't have any of these dots and I'm looking at a perfect line, is it possible for me to define that line using an equation? Absolutely. Y equals mx plus b. Would we have difficulties finding the value of n if it is a perfect line? No. Would we have difficulties finding b? The y-intercept? No. Perfect line. All you need is 2 points and you've got the model, which would be y equals mx plus b. X, b, but that is not b in statistics. But just to relate it to algebra, sure, I could find m and b easily with 2 points because it is fully deterministic. These observations, hard observations that I've recorded, 7 data points, they do form a linear pattern, but are they deterministic? No. Why? It's going back and forth. There is variability. Yes. What is causing this variability? Epsilon t. It is because we add that noise, that variation over the years, for our measurement, we end up getting variation in our model. So what we saw earlier, y equals mx plus b, which was deterministic, is no longer deterministic. Okay? So our goal in regression is to come up with a model that accounts for epsilon. That was back then. Regression. But so far, fitting that line's easy. We did it in regression analysis course. There is a problem with this scenario. Can you tell me what that problem is? Realistically speaking. Yes. Well, from a practical, realistic standpoint, whatever variation that we saw here, they aren't independent. So what do we mean by independent? Well, what happened here, the variation, independent of what's going to happen there. These two, these three, independent of that, they're all independent of each other. But no connection. Practically, then, that's not the case. Can you think of a scenario, well, that is not going to be the case? As an example, a situation.
Well, if we want to keep the number of babies, if we just move the timeline back like 5 or 10 more years, someone born in 1990 could be having children very easily by 2010.
Right. One explanation. Two. In the year 2000, people thought it was the end of this Y2K is going to happen, and we are doing. Some of you might be young for that to realize, but I've been going through this cycle when people say the apocalypse is here, doesn't happen. Year 2000, people were all freaked out, and they're like, the world is going to end, I'm not going to have babies, etc. And slowly things changed, they realized, well, it didn't end, I've got some leeway, so move on. Recession happened, and then people got frightened, and then they said, shouldn't have babies, recession. Years go by, got comfortable, and now we say, yes, more babies, right? So it seems like in that scenario, 1 year is somehow related to another. Do we agree? So the underlying assumption that we have in linear regression that whatever gets added, notice they are independent of each other, doesn't hold in all cases. They are no longer independent. So over here, independent is one word. What is the other term? Do you remember? Also starts with the letter I. I'll give you the second letter also. D. Silly. You can live in a den. That's called identical. Identically distributed. In short, we call this ID. And what is that distribution? We look for in linear regression. If you don't know what a distribution is that someone who doesn't? Think of, well, I don't want to give you the answer. I'll write it in a second. But independent, identically distributed, what is that distribution?
Could be a lot of.
It could be anything, but most commonly used,
I don't think you want to be uniform.
we don't want it to be uniform, agreed.
Normal distribution.
A normal distribution, we expect the distribution to be normal. It could be other things which require transformation, etc. But the easiest case, we want N stands for normal. What is new? Mean, what is sigma squared? Variance. Looking at that picture, do we believe that whatever variation or noise that got added in this graph could be normally distributed? So presumably, if it's not coming to you as to what a normal distribution is, they'll balance between both sides, 0, 1, or about 3. That said, do you believe that whatever variation that got added here is normally distributed? Could be, or not, why do you think so?
The distances above and below seem about the same.
So if you look at the points above the line, below the line, they seem to be balanced somehow. The line would form the mean, the average. So I've got some above, some below. That would mean the noise that got added here, there, just put it 1, 2, 3. Put them all together, it is going to be somewhat of a bell curve. Good? Great. Linear regression is okay from a theoretical standpoint, however, from a practical standpoint, not okay. Right? Okay. Forgotten the was series. Let's see. I'll leave that part to be like this. We all know what series is. Do we know what the series is? Copies. Some other bunch of things in the sequence. One reason. Another reason as to why we call it a series, because things move in a series. I'm going to take the same example. Should I give the same use? How will it work? Move that slightly over. When you draw this, it doesn't have to be aligned. Mine certainly does it, but what you have to know is that point is for 2011, 12, 13, 14, 15, 16, 17, 18, 19, etc. What experience? Y is the same. Y would be the number of babies born in the United States. X-axis, of course, is time. And it is time to get a bit crazy. So instead of calling it as y of t in time series, we simply refer to y of t as y sub t. Instead of calling it as epsilon t, we'll call it epsilon sub t. Later, I will change that notation of epsilon to a different letter. We'll get there. Same scenario, more practical, correct? So we started at 2011, there was a dip, people got comfortable, things went up and kept going up and up, and that is the year, so 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Yep. Not real data. Whatever happened in 2012, perhaps very likely to be related to what happened in 2011. Yes. Would it be fair to fit a line to this data? No, absolutely not. Can't be linear regression. Would it be okay to do non-linear regression? In other words, fit a polynomial or a curve of some sort? Yes or no? Yes. Curve. But should I do it? Do you follow my question? You can put this as a side note. Linear definitely adds to the question. Non-linear, sure. Curve. Is it correct? You can fit a model to anything, but if you fit the wrong model and make inferences, you're actually lying to people. So we've got to know if it is correct. Is it? Think about what I said there. Omar says no, Sydney says no. Why?
Because the epsilon sub t's are not dependent.
They're not independent, it's a big question.
I was just thinking, I mean, eventually it's gonna have to
Are you sure?
You not, babies are not gonna just like stop being born.
I mean, well,
I think
they are going to be born, but I don't think, it could, right? It could go back off, but given the state of conditions, I don't think that'll be a good idea. Year 2012 related to 11, 13, perhaps related to both 11 and 12, 14, related to 13, 12, and 11, one possibility, or just depends on 13 and 12, or just depends on 13. Regardless, they are related. Agreed. Okay. So it forms a sequence and we form a series. And that is a time series because we have a sequence of observations that occur over time. So is it correct? Absolutely not. Certainly, one can make an argument and say, well, sequence of observations over time, series of observations over time, hence time theories. But I don't think that is the reason why we call it time series, at least for me, the way I understood. Perfectly fine with calling it sequence of observations over time, series of observations over time, hence time series. Undergraduate textbooks, when they give this introduction, time series, that is probably the definition. Since you measure over time, we call it time series. That is not the exact reason, at least in my mind, the way I understood. I gave you a couple of scenarios. This scenario number one, whatever that happened in 2014. Depends on 13. Case one. Whatever happened to 14, perhaps depends on 13 and 12. Good. Whatever happened in 14 depends on 13, 12, and 11. Good. Should we pack our bags and leave? Now that we have that expression. Probably not. Definitely not. One reason, easy reason, well, if this is the model we are suggesting, whatever happens in 2014 is equal to 2013. Does the data satisfy that? No. Whatever happens in 14 must equal 13 and 12. Does it satisfy that? No. So that can't be. So something is happening over here, there, and there. Correct. I'll call it get used to phi and psi. You will see it a lot. What do I mean? Well, I'm not saying that Y14 or the number of babies in the year 2014 is exactly equal to the number of babies born in 2013. Rather, it is a weighted version of 2013. So this fee could be in a value. We will deal with that later, but some number. In a way, this sort of looks like regression. Do you agree? Y equals mx plus something, mx, previous observation. Roughly same over here. But in terms of calculus, I can simplify this and write it in a different way. What would I put?
Sum of VI.
Sum of these, right? Sideways and same over here. So I had a sequence, sum them to go to the next observation. I have a series. Sequence of observations measured over time, but explained using a series. That, I repeat in my own mind, is the correct definition of time series. Good. Okay. See the difference between the two? If you Google time series, some would use epsilon, some would use the letter Z, some W, it just varies a lot. I picked epsilon for today because that's what we did in regression standard notation. But what uses Z, commonly it is Z, we will get to that. Epsilon T. It's no longer independent. Yes. That in and of itself violates one of the important conditions of linear regression. We want the noise to be independent, identically distributed, not happening. Don't use regression. There. Great. In addition to that bit, (2014) related to 2013. Well, if that's got y and epsilon, excuse me, some x and the epsilon part, whatever that 2013 had its own epsilon gets added to 2014, correct? Y12 had its own epsilon, Y13 has its own epsilon, noise here, noise there, but 14 has its own noise, correct? Getting added together. Same, Y11 has its own noise, 12 has its own noise, 13 has its own noise, 14 comes into play, it has its own noise, but the noise or variability that is getting added in 14 is also connected to 11, 12, and 13. If I look at case 3.
So is it reasonable to say that over time, the noise gets greater because they keep on getting added onto each other?
Great question. Doesn't have to be greater, doesn't have to remain constant. The word that we are looking for, it has something to do with relate. Starts with the letter C. But contains relate. Correlates. The noise is not independent, rather they are correlated. So since we have correlated, not independent noise, regression, again, it's not going to work. But one thing that kind of works with both regression and time series and regression is epsilon t is normally distributed, but we take a special case, 0, 1. 0, 1 is standard normal in terms of noise. We call it white noise. Always seen that movie, White Noise. It's awful. I sat through it, but then I don't retain movies as long as really well. But all I know is it's an awful movie. But give it a try. There are other types of noise that we encounter. We have shock noise, which is the song. We have mid-distortion. These days, in apps, you will see sleep apps, and they have brown noise, green noise. It does count. So brown noise, green noise, they're all white noise variations. You just change mu sigma and you get white noise, but people fall for it.
I was just saying I listen to brown noise. A little bit.
Oh, you use brown noise?
I mean, not because I thought it was something different, I just like the one soundtrack that's called brown noise.
I see.
It just sounds like fuzz.
White noise, it has certain frequencies, and brown frequency varies, but the variations in frequency goes back to distributions. Short noise, we call it short noise because click, 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 click. If you listen to that series converted to an audio signal and you've got short noise, you know, you hear sounds that sound like gunshots. Are we clear? So that is basis for time theories.
Could you repeat your definition of time series with the second part of it on?
So are we clear with sequence of observations over time? Yes. Undergraduate textbooks simply replace the word sequence by series of observations measured over time series. But from a theoretical standpoint, I don't think that is the reason. 99% sure. Sequence of observations, but at any time step, whatever you measure is a sum of values in the sequence in the past. Sum of values in math, if you have a sequence, you sum them all together, that is a series. So time series. So we will be saying drunken M. Drunken M is sigma. M got drunk, fell on the curb, sideways M. Drunken M, easy way to remember. So in linear regression, we actually make use of the variation to fit the model. Do you agree? And good, I did epsilon, 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 and it's called least squares fit because we see how far the theoretical model is from, the average is how much does it deviate from the data points, and we use that, we minimize that, hence least squares fit. So noise is what's going to help us identify the model. If you are trying to weed out noise, same logic here. It is noise that we will use to model our data. Good. Okay. There are two cases of time series. Stationary time series, non-stationary time series. You can tell me if it is stationary or not. And I'll give you a hint. Think of regression and how to define, above, below average to get a normal distribution. Something like that. Yes. That is not linear regression. Reason being, drawing it this way, they are correlated. So time t, yt. Do we believe that this is stationary? Kelly?
Sure.
Why?
It looks pretty still, so that's why my guess would be stationary.
Still, the word, what is still? How are you capturing that still part?
Like, there's not a lot of like highs and lows, like it seems close to linear, so that's why I
Very
guess
good.
it's stationary.
So, if I draw a line, kind of a line, we've got observations about the line, below the line, the wiggles happened about that line, so it is stationary. The variation in noise, they are correlated noise, seems to wiggle around a still bonus, great word that Kelly used, remains still. So this is stationary. Can you think of another word for still? Don't tell me stationary. If something is in balance or equilibrium, very good. Things are in equilibrium, so we call it stochastic equilibrium. Imbalance, where stochastic comes into play, stochastic probabilistic. Great. In contrast, I have something like that. Varying with respect to time, YT. T. There is an underlying base level that I can come up with for that starter, for that answer is autumn, do you agree? Certainly it can't be this. Like if I have to draw a blue line, it's not that, right? It can't be that. Any thoughts on what it could be? It has to go up for sure. In a level. That is our mean level. But is it balanced? No. Too much here, too little here, kind of too much here, too much there. So the correlative noise doesn't follow a stable pattern about the mean. So that is not in stochastic equilibrium series. It's not stationary, that's non-stationary. Things you shouldn't do, just like in regression, you can't fit a nonlinear model for a linear data set and call it quits. You can't fit a linear model for nonlinear data and say, I did a great job. Same thing. You can't fit a non-stationary model for stationary data, vice versa. So the first thing to determine is whether the data is stationary or not. An easy way to do it, visualize. Always going back to the fundamentals of statistics, first step, look at the data. What does it tell you? That's your starting point. Once we identify, then there are ways to narrow down and identify which model is good for us. So within stationary models, we have a bunch of cases. Within non-stationary, bunch of cases. So you've got to make a choice and pick the best model that fits our data. Good? At least so far. Great. I have covered the basics, principles of time series, but what is the purpose? Why do we have to do all this? Who the hell cares, as I said? So I did principles, I did types. What is the purpose? Just for the sake of it, I'll put regression and time series analysis. Because that's how we started, we tried to connect the two together. Let's start with the easy case. You fit a line of best fit, at least twice line. What's the point? Who the hell cares? Why do we need it? To be able to predict. Take a guess. What are we trying to do?
Just predictions.
Prediction again. But only in this case, we don't call it prediction. It has a fancy word. Forecasting. You're not predicting, you are forecasting. Something that you cannot do with regression. We all know from undergraduate stuff, you cannot extrapolate your data in the sense you observe a bunch of values. Sure, you can make predictions closer to the endpoints of observations, even that is sketchy. So let's say you observe X values from 0 to 10, you can't use that data to predict what would happen at 20. Doesn't work that way. Fine. Time series, we can. Any thoughts, any guesses as to why it was omitted here?
So because the series like carries on the fact.
Very good. It is because as the series move along, the noise gets added over and over and added. And over time, since everything is correlated, I can make the argument that the next step is correlated to the previous, and 2 steps related to the previous values. So I can go forward. Objective is to measure that variability. So if I know that underlying line, all I have to do is add the variation, the noise, appropriately for, say, the future values. That will give me what we can expect in the future. Things will vary in the future, correct? Florida, hurricanes, spaghetti model, right? Simple time series. Well, I take that back. It's not simple time, it's a multivariate time series. Several factors influence at any time the forecast is made. Which one do you usually rely on? 2-day or 6-day?
2 days.
2 days, right? Great lesson learned last year, how things changed so fast. I personally would not leave my house until the forecast that I get the night before or 2 days prior. Good example last year, I said, it's not going to happen, I'm okay. I saw the 2-day forecast, I saw the 24-hour forecast, but, you know, I wake up somewhere around 12 hours and I have alerts, you have to evacuate. So things could change so rapidly in Northern hurricanes, even though they are time series, not easy. We're dealing with extremely non-stable waters. Same with earthquakes. Too noisy, completely non-stationary, prediction is difficult. So since we are looking into the future, we call it forecasting, and at the same time, we've got to be careful. If you know that you observed a process that depends on, say, 1, 2, 3 steps, you can't use that model to predict 18 steps ahead. Does that make sense? That is simply, a logical violation. If you only have knowledge and you know that the model goes 3 steps backward, a good statistician would say, well, let's go 3 steps forward and stop. I can't say, oh, let me just take it for 31 days, 10 days into the future. So, no extrapolation, no forecasting, nothing here, forecasting. But to what extent should we forecast? That will go back to the most effective. We will talk about that.
So if the data is not stationary, then what's the point of forecasting if the data is gonna be like very skewed from that time that we're looking at?
So, good question. There is an underlying need, even in non-stationary data. So the goal that we have in time series is to model that noise. Oftentimes, the accuracy is higher with the stationary model. But the non-stationary model, you can still do research on this. let's say we take right here. Overall, the series is not stationary. But in that neighborhood, that tiny interval, it's locally stationary.
Yeah, but aren't you relying on previous data for that, for those points anyway?
Yes,
So, how would that be reliable for you to like publish to like the public if it's not as accurate, let's say?
do you agree that that is local?
Yeah,
So I'm going to look at the entire series.
Yeah.
It could be, not stationary, but locally, it could be stationary. So I will work with that particular assumption. Once I get into autocorrelation, I will give two definitions, and that'll be a good place to stop. One, strong stationarity in the strong sense, and weak sense of stationarity. In practice, what we can achieve is weak sense. We cannot do strong sense stationarity. And when I give you the explanation, you will understand why. So I'm going for local stationarity, weak assumptions, so that I can do something instead of giving up, right? That is the simple explanation that I'll go with. Are we? Do we have a good understanding? When we come back, there are a few other things that we will do in terms of time series relating to different fields. I will list those. Did we take differential equations? So, okay. All I want you to do is look up one thing before you come to class next time. What is a dynamical system? That's all. I mean, you don't have to give me an essay, just the basic principle. What is a dynamical system? That's all.